Hi, I'm Henry Choi. In this slide, I want to talk about a brief introduction to machine learning. First of all, I want to talk about what is machine learning. Okay, how can we define it? And next, I want to talk about what kind of process we have to follow when we do machine learning, or what kind of components we have in machine learning activities. And I want to talk about how to categorize all the machine learning algorithms and applications we can expect with the machine learning algorithms. And I want to talk about a prerequisite knowledge for a machine learning study. Okay. Then, what is machine learning? So there is a textbook definition of learning by Tom Michel. And he said a computer program is said to learn from experience E with respect to some class of tasks T and performance measure P if its performance at the tasks improves with experiences. Okay, let me take an example about these definitions. So let's say we have a speech recognition system, which is a computer program, and we have experience, which is a data or speech signals. And the task is speech recognition, and the performance measure is recognition error, like a phoneme error rate or word error rate. Anyway, let's say just the speech recognition error. And if its performance improves with the experience, it means if the recognition error improves, decreases with the data. So whenever we get more data, more speech signals, then the speech recognition system improves. The speech recognition error rate goes down with more data samples than it is actually learning. Okay. Or we can understand this learning in a different way, like in Bayesian perspective. So in Bayesian perspective, learning is nothing but to update our confidence from prior to posterior. Okay, so let me put it in this way. So you have some thoughts on the machine learning before taking this class. Okay, then after taking this class, you actually have changed your thoughts on machine learning. That's learning. But even after taking this class, you didn't change your thoughts on machine learning, then you didn't learn anything, right? So that's what this statement says. And in this statement, actually, key factor is likelihood. Okay, so here's an equation. So this one is a posterior. And this one is prior. And this one is a likelihood. Okay, and let's say this W is your thoughts on machine learning, and the data is this class. You take this class. Okay, so before taking this class, you have some thoughts about machine learning, and then this means your thoughts after taking this class. You know what this means? PW given D means given D, what is the probability of W? So probability is actually something like understanding. Okay, so it's a little complicated. We're gonna get back to this point later, but for now, let's say this P is something like knowledge or understanding. Okay, so in this Bayesian perspective, we have a prior. Prior is independent of data. So before looking at any data samples, you have some thoughts about W. And this likelihood means when we have this W, so when we have some thoughts about the machine learning, then you take some class, then you try to understand what this class means to you, okay, based on your thoughts. And with these equations, this posterior says your thoughts after taking this class. So it goes from prior to posterior with data. Okay, this might be a little hard, but don't worry. We'll get back to this point later when we talk about the probability and the likelihood, etc. And we can understand the learning in different way too. So in general, so usually how do you learn something? So basically, we when we have something new, then probably we can read a book, right, to understand something. And then after reading some books, then you can try by yourself. So for example, uh, let's say we have a medical student and he learns something from textbook in class, from professors. Okay, so he learns something. Okay, so this knowledge is actually textbook kind of things in this analogy. And after these classes, and then with the medical license, and he actually do a medical practice, and based on the medical practice, then actually experience some things, right? And based on his experience, then he can learn something. That is actually data. So we'll learn something from this knowledge from textbook, and we'll learn something from our experience. So this is how we learn something. Okay, knowledge and data. But in deep learning, at the beginning of deep learning historically, like in 2012 or 2013 or so, then we just use the data, because if we trace back these arrows, then all the knowledge, all the information, everything is coming from data. So as long as we have enough data, then we can learn everything. That's kind of naive philosophy of deep learning. Okay, but if we are in the middle of this process, then we should be able to learn something from knowledge and the data at the same time. In the previous slide, we talked about the definition of machine learning, right? And in this slide, we want to talk about what is it actually in practice. When we have some problem, then we can actually solve that problem based on some rules, right? That's what we did in your programming homework assignment, right? So let's solve some problem, and then we have to implement some functions. And we actually provide all the rules to implement some things, but when the problem is really complicated, then this implementation is really complicated, and probably we might have lots of bugs in our code. Okay, and also designing nice rules or simple rules are really complicated, and it's not easy. And machine learning can replace those rules, because machine learning will learn and those rules automatically from data samples. Okay, here is a simple example. So it is a regression problem, and let's say we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 data samples. And for example, this horizontal axis is about math score, and the vertical axis is about science score, let's say, like physics. Okay, and usually when a student has a high score in math, it would have a high score in physics probably, but not all the time. So these are actual scores. So this guy has 10 and 10. This guy got like 50 and 45, and this one 70 and 43. Okay, so we have 11 students samples here, and if it is a regression problem, then we want to know the relationship between the math and physics. And so when our model is perfect, then finally we can estimate the physics score based on the math score. So let's say we have a perfect model. We know the relationship between the math and physics. Then when math score is 37. Okay, then what is the physics score? Can we guess? That's what this model does. Okay, then how to, we are interested in how to learn those such a model in this slide. So first thing is to make a kind of assumption about our model. Okay, so first of all, let's say the relationship between the math and physics would be linear. Okay, then this is our kind of the model. Okay, and x is math score and y is physics score, and a and b, these two variables are actually parameters. Okay, parameters means we have to train, we have to change these parameters to fit to these data samples. For example, given these data samples, then this line would be the best, right? So if this line is the best, then we can fix A and B with this line. If we have a really bad parameter values, then we might have something like this line. Okay, this line is not a great line, and this line cannot capture any kind of important features about the relationship between the math and physics, right? So if our initial model looks like this, then we have to change. We have to rotate these lines to be like this. Okay. So now we have a perfect parameter values a and b. Then we got this line. Good. But this line is not perfect to capture all the important relationships between math and science. Okay. Then what should we do? The problem is that the model is too simple to capture anything. Okay, so now let's increase the complexity of the model. So instead of a linear model, why don't we have a quadratic model? Then we have one more parameter. So now A, B, C, we have three parameters, and the model could be a little more complicated. Okay, then we can fit this model to the data samples, then we can find A, B, C fitting into these data samples. Then now this curve would be much better than this line. Okay, so if the problem is simple, then a simple model would be enough. But usually, in our real life, then problems are not that simple. So when the problem is complicated, then we have to increase the complexity of the model. Then there are many different directions to increase the complexity of the model. So not just polynomial equations. Sometimes we can have neural networks, sometimes SVM or decision trees, Bayesian networks. There are so many different machine learning algorithms. Okay, so what I'm saying here is that when we have a complicated problem, then we can solve that problem by increasing the model complexity. Okay, then we can fit the model to the data samples. Okay, if it is a regression problems, then it is actually a supervised learning. We'll talk about supervised learning later. And in this case, to train the model, we have data, okay, trained data like these 11 samples, and we have to estimate the parameter. In this case, A and B, these are parameters, or A, B, C. These three variables are parameters. Okay, and once we are done, once we have a trained model, then we don't have Y. Okay, then given X, we have to estimate Y. Okay, so that's basic kind of process in machine learning. Okay, and then let's compare traditional programming and machine learning. Okay, so I think you're already familiar with traditional programming. So from the data structure class or from Java programming class, then you know how to program, right? So when you do your homework assignment in such classes, then you know what to do, right? Then you have to implement some functions to implement some specific kind of modules. And then it means you have to provide a program. You have to implement the program by yourself. And then you can test your program by feeding the data into your program. Then you can get the output. If the output is not correct, then you have to debug. You have to change your program. Okay, this is kind of traditional programming style. Okay, but what is the difference between traditional and machine learning programming? So in machine learning, especially for training, we have data and output. Let's say this one is X and this one is Y. And then computer, actually this is two simplified diagrams. Actually we provide some hypotheses like, oh, the relationship between X and Y is linear. Then we have Y is AX plus B. Then we have to train A and B. Okay. Then given X and Y, then computer will generate program. It means the program means this one. Okay, this is the program. Okay, so we actually find the proper parameters, which is a program, and then after training, for testing, we use this program as an input and we provide a new test sample, and then the computer will estimate the output. So for testing, it's pretty much the same as traditional programming, but for training, it's completely different.